Good evening, everybody. Welcome to SLU. You are joining me, Paige Godfrey, for my Intro to Astro crash course. Tonight's course is about gravitational waves. And I apologize that it's not on its typical Wednesday night, but it was all for good reasons. I spent Tuesday, Wednesday this week up in Connecticut at SLU HQ, our headquarters, and I was driving home last night, when I was originally scheduled to give the normal Wednesday night course. But so here we are, Thursday night, and I appreciate you being flexible. And of course, you can always check this out on, well, I guess if you're listening now, then you wouldn't need to check it out after. So me telling you is kind of silly, but what I'm trying to say is that you can always check this out on our most recent live cast. So of course, you can always go back and re-listen to it or suggest it to a friend that might have missed it. But we are going to start off tonight with something a little bit special. So if you were with me about a month ago now, I guess, we did a galaxy classification course, and I suggested a kind of fun challenge, a little bit of a game to our members to go create your own Hubble tuning fork. So a Hubble tuning fork is a diagram that shows the different types of galaxies and the evolution of their shape, not through time, but through different ways that like the spiral arms look in spiral galaxies and the elongation of elliptical galaxies. So I suggested that you create your own Hubble tuning fork and share them with me, and I would share them live on this show this week. So we actually have our right here. Let me just switch on. If you're following along at slu.com, you can see my screen. So I'm sharing this in the live cast view as usual. And this is by our very own member Carol Botha. She did a fantastic job on this Hubble tuning fork. So if you want to see more about it and talk to her about how she did it, feel free to hop over on the discussion boards. There is a thread specifically for this with a lot of discussion going on. But congratulations to Carol. She did a wonderful job. So we start off here with our elliptical galaxies in E0, and that means it's a mostly spherical elliptical galaxy. And then it progresses through to an E7, which is a very elongated elliptical galaxy. We then move into our spirals, and we have our normal spirals, such as Andromeda, and the spiral arms start to spread out as you progress through SA, SB, or SC. But then we also have our barred spirals, such as the Milky Way galaxy. Ours is a barred spiral with a big bar running through the center. You can see this is a really great image to see the bar coming through and the spiral arms coming off of it. And I love that she has put the intermediate galaxies on here as well, where ones that kind of look like they're a little bit of both. Like they almost look like a normal spiral, but then they might also look like there's a bar running through the center. So really fantastic job, Carol. We're very proud of you. And anybody else, if you want to, there's some traction in this thread about people that are still working on this challenge. So if you finish it up, feel free to share your images with me, and I'll share them over the course of, these coming weeks and shows, and we're happy to take a look at them. And I'm really excited about this. So thank you so much for participating, Carol. And actually, just a fun little tidbit of information while we're highlighting Carol here. She just announced to me on Twitter that she just upgraded to astronomer member level, and we are so grateful for you, Carol, and your continued support, and we're excited. This is perfect timing because what we have coming up this month is the Messier Marathon. So if you're not familiar with it, hop over to our homepage. You can read all about it in our discussion boards, and we have when this loads, you'll be able to see there's a card on the homepage that describes the Messier Marathon, but as I say every week, my computer is super slow when I'm trying to stream it, so it doesn't always load well. But you can go into our community discussion boards and look at the Messier Marathon thread and learn all about it. Basically, we're spending a whole weekend making all of these reservations to objects that are in the Messier catalog, these bright objects, and making mosaics out of them. So it's going to be a really fun time. We encourage you to participate, and certainly it's easier if you are an apprentice or astronomer level, and so great timing, Carol. Okay, so let's get going on tonight's topic, which is gravitational waves. So pretend the year is 1916, and Albert Einstein is devising his theory of general relativity. This includes the idea of gravitational waves or ripples in the fabric of space-time. Fast forward nearly 100 years, now it's 2015, and astronomers announced the first physical detection of gravitational waves, proving Einstein's theory with concrete physical evidence, revolutionizing the entire field of gravitational astronomy. Incredible. Mic drop. So let's back up and review what space-time is. When we think of gravity on Earth, we don't really think about the space-time continuum. We think about like an apple falling from the tree, on Isaac Newton's head, being pulled towards Earth's surface. We stand on Earth's surface because gravity tugs us down towards the surface. But what's really happening? Why do things like the moon have less gravitational pull, like a weaker gravity force than on Earth? So this all has to do with mass. So the Earth is more massive than the moon and therefore has a larger gravitational pull on it. The atmosphere plays a role in this too. And the mass of an object, this is where the space-time continuum comes in. So we have 3 dimensions of space, x, y, z. And we have 1 dimension of time. Now we know that spatial dimensions move backwards and forwards. Certainly you could walk forward or backward in your x direction, go up or down in your z direction. But the time dimension only moves forward. This is the whole issue with trying to travel through time and why we don't believe that there are time travelers yet. But if you combine these 3 spatial dimensions and 1 time dimension, we have the 4-dimensional space-time continuum. And the reason we combine them is because we think that they're connected. And so when you have a mass that is heavy in the space-time fabric, it has a larger pull on it. So what I'm sharing with you is kind of an artist rendition of this space-time fabric. So imagine you and a friend were holding the 4 corners of a bed sheet. Okay, and you throw a marble onto the bed sheet. It's going to make a little bit of a dent, right? It's going to pull down a little bit, not a ton. Now, what if you threw a bowling ball onto the sheet? Well, that's going to make a huge impact on the sheet. It's really going to tug down in the center there. So this is kind of what's happening in the space-time fabric. So certainly space-time is not this planar sort of distribution, but it's 3-dimensional. But this is a good example of how heavier masses have more of an effect on the fabric. So if you can imagine that this is all enclosed, and so the bowling ball really has this deep effect on the space-time fabric. If I tossed a marble in here, it's going to orbit around and around. You ever see those like really big coin fountains? You toss the coin in and it spirals all the way down to the bottom. So that's kind of the idea here. And if you have a weaker central mass, then the orbit around it is going to be much weaker. So this is kind of the gravitational pull that's happening in towards the center of the mass. So this is what we call the space-time curvature. So any object that has mass that accelerates, accelerating meaning that it changes its position at a variable rate. This includes spinning or orbiting. We know that if we move in a circle, we have an acceleration because our position is constantly changing at a variable rate. So any object with mass that accelerates produces gravitational waves. So we, humans, and cars, and airplanes, we all produce gravitational waves, but they are way too small to be detected. In fact, it's actually not even possible to build a machine that could spin an object fast enough to produce a detectable gravitational wave. The strongest materials we know of would break apart at rotation speeds that would be required to make a gravitational wave that's detectable. So since we can't generate gravitational waves that we can detect, we need to look in places in nature where they are created naturally. And so we are looking out into the universe where we have really violent, energetic phenomena that would create a gravitational wave that could be detectable to us. So an extremely energetic process occurs, like the collision of two neutron stars, or two black holes, or a black hole and a neutron star, or a supernova, something incredibly energetic and violent that releases a bunch of energy, and some of this energy actually disrupts the space-time fabric, sending ripples through it, like if you skipped a rock in a lake and you see the water waves that emanate out from the rock. These are the kind of gravitational waves that we're talking about. So in this fabric, if I had two of these bowling balls that were orbiting one another and they collided, they would send out a huge amount of energy, and it would literally ripple the fabric of space-time gravitationally. So these waves travel at the speed of light, and they are broken down into, they have been broken down into 4 different types of gravitational waves that we can expect to look for. So when we build instruments, and I'm going to talk about one of the main gravitational wave detection instruments out there, but when we build instruments, we really need to know what we think we're going to be looking for in order to be able to build something appropriate. So astronomers broke gravitational waves down into 4 categories so that we could predict the kind of signals that we think we should be looking for. The first one is called a continuous gravitational wave. So it's something like a very rapidly spinning neutron star. So a neutron star is a really dense stellar remnant. When a massive star goes through its lifetime, it evolves through the main sequence, and then it puffs up and it explodes in a supernova, and you're left over with a really dense core, many, many times the mass of the sun, but much, much smaller, like the size of a city. The actual neutron star is only like several miles across, and so it's an incredibly dense object. And so when they're rapidly spinning, they can put out gravitational waves if there's any sort of changes in their spin, any sort of deflections, anything that causes an acceleration, it would send out a gravitational wave. So we call this a continuous gravitational wave because we would expect to see it occurring over and over again. Then there's compact binary inspirals, such as 2 neutron stars, 2 black holes, a black hole and a neutron star. So when these things collide with one another, the collision creates this enormous amount of energy that gets sent out in like a shock wave through space. We also have what we call a stochastic gravitational wave. So these are gravitational waves that we don't know what to expect. So they're stochastic because they statistically can't really, they're a randomized pattern of gravitational waves that can be analyzed statistically, but we can't really predict what they're going to look like. So if there's an event that we haven't, thought of yet that could produce gravitational waves, we would expect to detect it, but we don't really know what we're looking for. So astronomers have to be prepared that, when they subtract all the noise out from detecting gravitational waves, like vibrations such as like earthquakes and weather and things like that, we subtract out all that noise and we want to make sure we're left with the signal that we know for sure what it is. So we have to plan that there might be signals that are gravitational waves, but we don't know that they are right off the bat because we don't recognize the pattern. And then the 4th category is called burst gravitational waves. So this would be an event that would just send off a big, large gravitational wave that we also don't really know what it would be, but we would see a spike in the signal and we would expect that this must be a gravitational wave. So we have these 4 categories. Basically, 2 of them are which ones we can really well predict what the gravitational wave signal is going to look like, and 2 where we can't. So moving forward, this is how astronomers built the gravitational wave detectors. If we go back to 1974, just about 20 years after Albert Einstein died, 2 astronomers working at the Arecibo Radio Observatory in Puerto Rico discovered a binary pulsar system. Now, to remind you, a pulsar is a neutron star where the magnetic field pulses are being sent off into the direction of Earth. So when a neutron star is rotating about itself, if it has a high magnetic field, coming off the poles are these flares of radiation. And when those flares are orbiting in a direction that hits Earth, picture like a lighthouse. Every time the object rotates around, we see this flare. We call it a pulsar. So this pair of astronomers discovered a binary pulsar system. And so this was the type of system that, according to general relativity, should radiate gravitational waves. But now this is 1974, and we said we didn't detect the first physical evidence of gravitational waves until 2015. But astronomers began measuring the period of these pulsars' orbits and how it changed over time. So because the pulsars are sending these radiation beams in our direction every time they rotate, we can watch their rotation and we can watch their orbit around one another. They're basically shining a flashlight on us like, hey, look at me. So we measure their orbits, and as they change over time and as they are in-spiraling, it took 8 years of observations, and then it was determined that these pulsars were getting closer to each other at precisely the rate that is predicted by general relativity. This system has been monitored now for over 40 years, and the observed changes in the orbit agree so well with the prediction from general relativity that astronomers say there's no doubt that this system would emit gravitational waves. So this was the first indirect proof that gravitational waves would exist back in 1974. Now, LIGO, the Laser Interferometer Gravitational Wave Observatory. I challenge you now to say that 5 times fast. But LIGO was built to detect gravitational waves, and it consists of 2 really widely separated interferometers, both in the United States, one in Hanford, Washington, and the other in Livingston, Louisiana. Each interferometer is in the shape of an L with 2.5 mile arms extending from the base. So each interferometer has these 2 arms that are both 2.5 miles long, and both interferometers are connected. They work in sync with one another. So on September 14th, 2015, for the very first time, LIGO sensed distortions in space-time caused by gravitational waves. And the source of these gravitational waves were 2 colliding black holes 1.3 billion light years away. That means that that event occurred 1.3 billion years ago. Gravitational waves travel at the speed of light. So when something is 1 light year away, a light year is a distance that it takes light to travel in 1 year, because the speed of light is finite. So since gravitational waves travel at the speed of light, if the black hole collision was 1.3 billion light years away, then that means the collision occurred 1.3 billion years ago. So we're getting gravitational waves that are 1.3 billion years old. The black holes that collided were about 29 and 36 times the mass of the sun. Huge, huge black holes. By the time that the gravitational waves from the first detection reached LIGO, the amount of space-time that they rippled through was thousands of times smaller than the nucleus of an atom. Thousands of times smaller than the nucleus of an atom, and we detected it with our laser interferometers. So what was happening in an interferometer such as this? There are laser beams that are shot out along these 2.5 mile long arms, and at the end of the arm is a mirror, and it measures how long it takes for the laser light to reach the mirror. When a gravitational wave comes through space, it distorts the space-time of these arms, and it makes one arm a little bit longer than the other. So if you're watching my mouse, pretend the wave is coming in this way. The wave comes through. It doesn't affect this arm because the wave ripple is just passing right through this arm. But this arm here, it's going to extend the length of the arm by just a teeny little bit. And so while normally the laser light would hit the mirror of this arm and the mirror of this arm at precisely the same time, because the gravitational waves made this arm a little bit longer, it took a little bit longer for the laser light to reach the mirror. And so the difference in kind of think of it like a stopwatch. If you have two racers running and they're running at exactly the same speed, but then you make the track just a little bit longer for the one runner, your stopwatch is going to take just a little bit longer to measure when that runner crossed the finish line. That's kind of what's happening here. So this is how they measure gravitational waves. And of course, they've accounted for, Earth processes that would cause vibrations from light, vibrations from sound, earthquakes, things like that. Of course, they've accounted for all of that. So they're really able to pretty confidently say that the results are from deep space gravitational wave sources. So the first detection was in 2015, and it was two black holes merging. Now, we've had more detections since, and there's been 4 more binary black hole detections since the first. So we're at a total of 5. But also, back in 2017, in August of 2017, so about 2 years after the first binary black hole detection, they announced the first detection of gravitational waves from a pair of in-spiraling neutron stars. So it's really cool that not only were they able to detect gravitational waves at all, right? Like, let's not forget the impact of this detection, but to have being able to detect it from 2 different types of processes. So electromagnetic emission from the collision of the neutron stars was observed in multiple wavelength bands as well. So this was the first time that they didn't just detect the gravitational waves alone, they also detected the electromagnetic emission from the neutron star collision. We saw the light from this neutron star collision, really being able to verify that the gravitational wave detection came from this source. This was, again, in August of 2017, and it's the first time that a cosmic event was observed both with light and gravitational waves. So cool. So gravitational waves, by studying them, it gives us an entirely new look of the universe. So what's really important about the neutron star collision is, for me at least, that we detected it both with light and gravitational waves. When we normally study phenomena in space and objects, we're looking at the light, we're looking at the electromagnetic radiation. But light is heavily affected by matter in the universe. We have gravitational lensing, which is the topic for next week's course. But then we have it goes through gas and interstellar dust and clouds. It gets absorbed and re-emitted, and we are gravitationally lensed, and so our atmosphere on Earth affects the light that reaches us. And we do our best to account for these things, but gravitational waves very weakly interact with matter and therefore reach us pretty much unimpeded. It's really incredible to be able to study these, especially in conjunction with light from the same source, such as this neutron star collider. The LIGO detection, the very first one, that was the binary black hole collision. So not only did that detection confirm gravitational waves and prove Einstein's theory of general relativity was correct, it was also proof that binary black holes actually existed. Up until then, we didn't know for sure that binary black holes existed. Remember, black holes don't put off radiation the way that stars and things do. We can see their effect on light because we can see how light is gravitationally distorted around them. But to actually observe black holes is incredibly, incredibly difficult. We can't even see the one in the center of our own galaxy. We just see how the stars around it are affected. So this was the first proof that a binary black hole system actually existed, and also that black holes with masses about 30 times that of the sun also existed. We hadn't had proof of that yet either. We knew that both from theory that these binary systems and black holes that were 30 times the mass of the sun were possible, but neither of these facts were known for sure before this first detection in 2015. Really super cool. So if we go, this is a great site if you want to read up some more about LIGO and everything. I mean, ligo.caltech.edu has a lot of valuable information. What I'm going to play for you now is a video of the detection, it's just like a animated video, but it's an animation of two neutron stars as they orbit each other and then coalesce into one object. Let me see if I make it full screen. Can you see that? Yes, I think you can. Cool. So I'm going to play this. And so we're watching here the neutron stars orbiting one another, and it's hard to see at first, but they are in-spiraling. In spiral means that as they orbit one another, they are getting closer and closer together, that the distance between the two objects is decreasing. And so you can see the speeding up right now of the in spiral and more gravitational waves being created, all this radiation streaming away, and there's the collision and the ripple effect. And now we're left with one object because the two collided with one another. So what happens is, and I talked about this a little bit last week with the fast radio bursts as well. So these objects are in-spiraling. The closer that they get to one another, the quicker the in-spiral begins to happen. Okay, I'm back. I apologize about that. So my computer has been giving me some trouble lately, and I think it's kicking the bucket. But let me just take a second to double check that you can actually hear me again. So what happens is collision and the ripple effect. And now collision and the ripple effect. And now we're left with one object because the two collided with one another. So what happens is, and I talked about this a little bit last week with the fast radio bursts as well. So these objects are in-spiraling. Okay, I'm going on the assumption that you can hear me, so I'm just going to keep talking. Hopefully I'm not talking to myself. That's awesome. Anyway, so, okay. Yes, you can hear me. I've just confirmed it. Great. Okay, so let me put my screen back up so that you can see what I'm doing. Okay, so we were watching the video of the in-spiral, and the in-spiral speeds up as the objects get closer together. So if you pretend you have your sheet with your friend, you're holding the four corners of the sheet, and you toss, mechanically this might actually not work with a bed sheet, but just picture it with me. So you toss two tennis balls onto the sheet at the same time, and they start to orbit one another, and the closer that they get to each other, the bigger that gravitational pull in that one area, as opposed to their weaker gravitational pull separately, right? So these objects are getting closer and closer, and the larger their gravitational pull accelerates their in-spiral, their infall into one another. And then we talked about this last week with fast radio bursts. Right the millisecond before they collide, they send off this huge amount of energy, and this might be where fast radio bursts, or some of them, come from. And then we also get the gravitational waves. So this is just another way that detecting gravitational waves and studying them can really advance the field, because of things like fast radio bursts, where we have these super energetic bursts of radiation that are very quick and we don't know where they're coming from. We have theories, but being able to detect maybe that a fast radio burst occurred at the same time as a gravitational wave detection would just be incredible. So moving on a little bit, there are some fun facts on this LIGO page that I really enjoyed reading, and so I was just going to share a couple of them with you. The first one is that at its most sensitive state, LIGO will be able to detect a change in distance between its mirrors 1 in 10,000th the width of a proton. This sensitivity is equivalent to measuring the distance to the nearest star to an accuracy smaller than the width of a human hair. That's how sensitive these laser interferometers have to be in order to detect things like gravitational waves. Because remember, Gravitational waves are so weak and indetectable, we don't detect them from any sort of Earth-generated event, but even events like the merging binary black hole system from 1.3 billion light years away was so weak by the time it reached us that the space-time wobble that it generated was thousands of times smaller than the nucleus of an atom. So another really cool fact is that the arms of LIGO, these 2.5-mile long tubes that the lasers run down, are long enough that the curvature of the Earth was a factor when they had to design the instruments. So over the length of the arms, the Earth curves down away by about 1 full meter. So they had to be really precise with the way that they leveled the area and to counteract this curvature, because LIGO's arms need to be level. Without this, the lasers, which travel in a straight line, of course, would arrive 1 meter above the mirror if they didn't account for the curvature of the Earth. So there you go, flat earthers. The Earth is round. So studying gravitational waves really gives us a whole new way to look at the universe, aside from just electromagnetic radiation. But using gravitational waves in conjunction with electromagnetic radiation are really what's going to advance astronomy and the way that we look at the universe. Someday, gravitational waves might even allow us to listen to what was happening in the very, very beginning moments of the universe, when it was so dense and hot that no light could move around. We don't detect any of that light. If you heard my cosmic microwave background course a couple weeks ago, I talked about this wall where we can't really see beyond it, this wall of CMB radiation. We can't see beyond it because the light wasn't scattering around at that time. And so any photons emitted were absorbed immediately by a plasma of hot ions, because the universe was so dense when it first began. But gravitational waves from that time could travel directly to us on Earth with very little interference from all of the matter, because, as I said, gravitational waves interact very weakly with matter. So if we can detect gravitational waves from the earliest moments of the universe, it would tell us so much about what happened just after the Big Bang, so much that we don't know because we can't detect the electromagnetic radiation from that time period. Next week, we'll talk about this gravitational lensing that I mentioned earlier and the way that matter in the universe affects light and affects how we see light, but also in good ways. So it's not just bad that it affects the light that travels to us. It can help to magnify the light, and how it gives us a rare view of the universe that we might not see if something was in the way of the light traveling towards us. And could this gravitational lensing be used as a way of communication? So in the meantime, you can look forward to Sunday night. We have Paul Cox, as usual, with Practical Astronomy. And we also have a special live cast with Paul to learn about the upcoming March Messier Marathon that I mentioned earlier. That's coming up on March 17th. So if you want to hear more about it, you can go over to the discussion board area and read about it. And you can also tune in to Paul's show on Sunday night and hear more about it. So thanks for listening. Thanks for being patient through the shutdown of my computer. And I hope you have a great week, clear skies, and join me next week to hear about gravitational lensing. Create your own Hubble tuning fork and share them with me, and I would share them live on this show this week. So we actually have our right here. Let me just switch on. If you're following along at slew.com, you can see my screen. So I'm sharing this in the live cast view as usual. And this is by our very own member, Carol Botha. She did a fantastic job on this Hubble tuning fork. So if you want to see more about it and talk to her about how she did it, feel free to hop over on the discussion boards. There is a thread specifically for this with a lot of discussion going on. But congratulations to Carol. She did a wonderful job. So we start off here with our elliptical galaxies, an E0, and that means it's a mostly spherical elliptical galaxy. And then it progresses through to an E7, which is a very elongated elliptical galaxy. We then move into our spirals, and we have our normal spirals, such as Andromeda, and the spiral arms start to spread out as you progress through SA, SB, or SC. But then we also have our barred spirals, such as the Milky Way galaxy. Ours is a barred spiral with a big bar running through the center. You can see this is a really great image to see the bar coming through and the spiral arms coming off of it. And I love that she has put the intermediate galaxies on here as well, where ones that kind of look like they're a little bit of both. Like they almost look like a normal spiral, but then they might also look like there's a bar running through the center. So really fantastic job, Carol. We're very proud of you. And anybody else, if you want to, there's some traction in this thread about people that are still working on this challenge. So if you finish it up, feel free to share your images with me, and I'll share them over the course of, these coming weeks and shows, and we're happy to take a look at them. And I'm really excited about this. So thank you so much for participating, Carol. And actually, just a fun little tidbit of information while we're highlighting Carol here. She just announced to me on Twitter that she just upgraded to Astronomer member level. And we are so grateful for you, Carol, and your continued support. And we're excited. This is perfect timing because what we have coming up this month is the Messier Marathon. So if you're not familiar with it, hop over to our homepage. You can read all about it in our discussion boards. And we have... when this loads, you'll be able to see there's a card on the homepage that describes the Messier Marathon, but as I say every week, my computer is super slow when I'm trying to stream it, so it doesn't always load well. But you can go into our community discussion boards and look at the Messier Marathon thread and learn all about it. Basically, we're spending a whole weekend making all of these reservations to objects that are in the Messier catalog, these bright objects, and making mosaics out of them. So it's going to be a really fun time. We encourage you to participate, and certainly it's easier if you are an apprentice or astronomer level, and so great timing, Carol. Okay, so let's get going on Good evening, everybody. Welcome to SLU. You are joining me, Paige Godfrey, for my Intro to Astro crash course. Tonight's course is about gravitational waves. And I apologize that it's not on its typical Wednesday night, but it is all for good reasons. I spent Tuesday, Wednesday this week up in Connecticut at SLU HQ, our headquarters, and I was driving home last night, when I was originally scheduled to give the normal Wednesday night course. But so here we are, Thursday night, and I appreciate you being flexible. And of course, you can always check this out on, well, I guess if you're listening now, then you wouldn't need to check it out after. So me telling you is kind of silly, but what I'm trying to say is that you can always check this out on our most recent live cast. So of course, you can always go back and re-listen to it or suggest it to a friend that might have missed it. But we are going to start off tonight with something a little bit special. So if you were with me about a month ago now, I guess, we did a galaxy classification course, and I suggested a kind of fun challenge, a little bit of a game to our members to go create your own Hubble tuning fork. So a Hubble tuning fork is a diagram that shows the different types of galaxies and the evolution of their shape, not through time, but through different ways that like the spiral arms look in spiral galaxies and the elongation of elliptical galaxies. So I suggested that you